I guess what I want to say here, let me go back. So if I show you this slide, it's pretty easy to understand. Hey, yeah, I know what you're doing. I know how to make changes to it. But the question is, hey, how'd you find this? You know, the binary is huge. How did you get to this one particular spot where it was obvious? And the answer is PyMay will do that for you too. So what you do is you put PyMay against Safari, you browse a bunch of sites, try to avoid the ones that have PNGs because that's what we care about. It turns out porn sites don't have a lot of PNG images, so you're pretty good to go. And what happens, you just keep going and going and going until there's no more breakpoints. Which means you've executed and recorded a lot of code that has nothing to do with PNGs. Okay, then you save that, and you do it again, except this time you only look at stuff that has a lot of PNGs on it. And you record what you get there. If I filter out the first run from the second run, you're left with only the code that has to do with PNGs. And you very quickly zoom right in on that code I showed you. So what happens? Well, in this particular deal on Safari, there were 123,000 basic blocks. When I was just surfing, it was 12,000 of them got hit. When I was looking only at PNGs, it was only 1,000. So I already narrowed my search time to only 1,000 basic blocks. And by looking at those, you can very quickly, so it's only less than 1% of the total basic blocks I'm able to look at, and I'll quickly find that spot in the code I showed you. And these yellow ones are the ones that show up just when I was surfing. Okay, so what's the only drawback with PyMay? Well, PyMay works from IdaPro, so if IdaPro messes up, PyMay messes up. If you're trying to get code coverage for some binary that has anti-debugging stuff built into it, you're probably going to have problems because PyMay is essentially a debugger. You kind of have to know what DLL you're interested in, or you have to load them all, which is like a pain. So it's sort of a chicken and egg a little bit, but if you're in the worst case, you just load everything, it just takes a little longer. And in this case, I had to set 123,000 breakpoints, and anyone who saw my lecture yesterday knows that takes like 10 minutes. So it may take a while. Alright, so, I showed you like how you can imagine getting better code coverage. Now I'll show you how you actually do it. Basically 3 ways: manually, dynamically, or from the binary. So I kind of explained manually how you do it. This is just a zoom in on that other slide. You can see right here, well, there's a jump that I didn't take. And, trace back to compare. Oh, look, there was a byte. I should have said the PLTE, and then that would have been in business. So let me show you one more example. So FreeCiv, this is like, fun multiplayer game. And like I said, don't ever run it on any computer that you actually care about because it's fun. Okay. I want to fuzz this thing, and I want to show you how I get better code coverage from it. So how do you do it? With the binary, put it in IdaPro, get the PETA file, launch the program, attach it to PyMay. If you want, you can filter out what happens just with like more net padding to it, but that's not even necessary. And then you start fuzzing. PyMay will tell you when you hit. To fuzz it, I use the tool called GPF, written by Jared DeMont. It's a good little fuzzer. It's a utility-based fuzzer. Works on PCAP captures. So you fuzz FreeCiv. That's the lines you want to do it. What's the problem? The first problem we run into is if you try to connect to FreeCiv more than like 3 times in a minute, it doesn't know what to do. So it's not like a really good program to fuzz. So I had to build in like all these sleeps to the GPF. It took a lot longer to fuzz. I went to bed, woke up the next morning. I had 96 functions during my fuzzing. I looked back in IdaPro to see if I could do better. I found this humongous switch statement. And I only hit one switch. So I know I can do better, right? I traced it back to see where that data came from. It turned out it was the 3rd byte in my packet controls that gigantic switch. I said, okay, I know what to do. At this point, I was basically just sending more or less random data. I figured out the 3rd byte's important, so I'll make sure that GPF modifies that 3rd byte a lot while I was doing it. So I've taken what used to be random by using code coverage. I figured out a little bit of the structure of the packet, and I'm going to use that to my advantage. So there's another GPF line you can run. Now I got better coverage. The first time when it was more or less random stuff, I got 614 lines, or basic blocks covered. This time I got 2,300 basic blocks, so I did much better. And I did hit every case in that switch statement. Still, I didn't find any bugs, though, right? So, code coverage is academically cute, but if you don't find bugs, you're going to get fired. This time won't. So this is just reiterating what you do is you send random data, you look at code coverage, you figure out a little more structure. and then you send some more random data with that structure, and you keep going. Okay, so I said, okay, I know about the third byte, so now I want to fuzz the rest of the packet. I do that here. I started, I started fuzzing it, and I immediately, the thing just like 100% CPU egg. So I found some sort of memory corruption bug. Not that big a deal. So then what I did was I started fixing the third byte, and then fuzzing the rest, and doing the same thing over and over. Eventually, hours later, I eventually got the byte, setting the third byte to 0x47, so hex 47. And then, so it's hex 47 and then random stuff. And I looked at the code coverage, and I saw this. Okay, well, I missed a couple basic blocks here. Has a mem copy in it that I missed, and I like mem copy, so I'll make sure I hit that next time. Heap overflow. So there's a particular packet that if you send a preset server, it'll fall over on its face. So link the packet. The third byte's important, 2F. The 0C got me down that other left branch. Then a length of a mem copy, any size you want, into a fixed length heap buffer, and then data. And make sure you send up data because it doesn't check how that you sent too much data, but it definitely checks if you sent too little. It won't copy it. Right. So, it's bugging preset, not that big of a whoop. It's fun for your friends and stuff, but there's this thing called meta server that's kind of cute too. It tells you all the preset servers in the world. So it does your targeting for you. Not that you would necessarily hack all these preset servers, but now you could. I'll finish here and I got like 5 more minutes. Is that fine? Okay. So I sort of skipped over some of the boring parts of my job, which was I started on byte 0 and then moved to byte 1 and then 2. And eventually I got to 47 X, which is actually 47. And there's actually no guarantee I was ever going to find anything, and it was kind of boring. So there's got to be a better way. It's, as I say, time intensive, aka I was going to shoot myself. So the idea is you want to automate what I was doing. So Autodat kind of does that, but I prefer another shared tool called EFS. So it's basically a combination of time day and genetic algorithms. And what are genetic algorithms? Well, basically it's a tool that solves optimization problems approximately. All you need to do is say what the fitness of an organism is, how two organisms recombine. Sexy math. And then how one organism can mutate itself. And if you see all those things, you throw it into the genetic algorithm and it'll spit out an approximation. So, real quick example, there's a function. I'll say that two numbers combine by this concept called single point crossover, which means you write out the binary representation, randomly pick a spot, take the left half of one and the right half of another, and you get your new number. For mutation, I'm just going to flip it 10% of the time. You get, this is just a slide where you can see the numbers progressing as time moves on. If you solve this thing exactly, it's 5,000. Let's see how the genetic algorithm does. Well, you can see as time went on, it basically just sort of narrowed it down 5,000. So, yeah, it kind of works. So now you believe that the genetic algorithm works. Okay, so how does EFS work? Well, EFS needs, if it wants to use a genetic algorithm, it has to define those exact same things. So it needs a fitness function. How fit is, in this case, the test case. And it turns out it has to do with how many lines you code covers. Makes sense. I've told you how great code coverage is, so I should totally agree with this. They choose the most fit individuals to recombine them. And then, I don't know how real genetic algorithm scientists can illustrate this with that kind of stuff. So they use single point crossover for the packets or the test cases or whatever you want to call it. And the only thing that's super clever about it is Jared actually respects the tokens in the packet. So he doesn't interrupt. Like if 4 bytes are for a size, he doesn't split it right in the middle of those 4 bytes. He'll only split it on the ends. And then for mutation, he adds fuzzy heuristics. Okay, so there's a screenshot. EFS. So you run it the same way as time A, basically. Does it work? Well, yeah, kind of. So here's an experiment I ran. This is the preset experiment again. And if you see this top line, this is the number of lines covered by the most fit test case. So I started with some test cases. I only covered, 47 lines, and by the end, I was covering So I did actually, without doing anything, on test cases that were twice as effective as the previous ones. Static algorithms aren't perfect. EFS definitely isn't a perfect implementation of them, so it's not perfect, but it's better than sitting there and doing everything I can. I'm just going to skip this part. I'll tell you why, and then I'll skip it, but please talk to me afterwards. So the final solution is you take a binary, and obviously there's, you can analyze the binary and figure out all the different code paths just statically, and then try to figure out by hand exactly what inputs you've got in that result. Right? So EFS are trying to do this approximately by saying lots of test cases and then tweak it. You got the binary sitting in front, you just look at it, right? So people have done this. Microsoft did it. At least they say they did in a paper. They don't release their tools. Catchcode, there's a tool built on Valgrind that kind of does this too. HP Gary kind of has something that does this, supposedly, but again, no one releases this tool. So what you would have to do to solve this type of problem is find where the data enters, symbolically figure out all the different paths for the program that you can possibly hit, and the dependencies in the middle that have to do with what your input was. And then these get solved. This is like the 30-second version of my talk here. So it turns out here's a little program that has 3 paths through it. Here's the constraints. So you want to define, a normal program would have like 1,000 constraints. You can imagine the preset one was like type 3 equals 47, type 4 equals C, and so on. So there would have been like 6 constraints for the preset bug. And then there's this, you can use a program that would solve these constraints. So, and on that little sample, I used the program, and it found 3 test cases that really did it. So I was running for it. I have no idea how it does it. It's like magic, but those really exist. And again, talk afterwards if you're interested in how it works. So using that, you could find sophisticated bugs like preset without ever. So I found that without ever running the binary. And you can also use that if you're sick of fuzzing at some point. That to you find the places that you haven't hit with fuzzing, and you can at least do stack analysis. Alright, so what's the point of the whole talk? Fuzzing sounds really easy until you try it. When you actually try it, you run into a lot of problems that no one ever told you about, but now I've told you about them, and I've told you some ways to hopefully solve them. Code coverage isn't perfect, but it's a tool you can use to try and improve your fuzzing. You definitely will not find any bugs in code that you have never executed. No one will argue with that. Increasing code coverage can be difficult and time-consuming, but there's tools coming that's going to make your life easy. And that's it.
Are your slides going to be up too?
Yeah, I'll have everything there for you. So, yeah, skip some good ones. Yeah, just see me after.